Hi, today we're doing the 5152 review notes. This is a collection of problems that has different kinds of techniques and processes that we've learned as we work through 5.1 and 5.2. Remember, 5.1 is the simplifying and 5.2 is the verifying. So the first thing I want to do is talk about these problems because I want to look at how they're written. Oftentimes students miss questions on assessments in this topic because they don't pay close enough attention to what the directions are asking them to do. So the first one says rewrite 1 over 1 plus sine x so that it is not in fractional form. So that's another way of saying simplify, but there's a little bit of a catch there because it's saying in the end, when you're finished, the goal is to not have any fractions. So you want to rewrite and work through the simplifying process until you don't have any fractions, and then you would stop the problem. The second one is just a straightforward simplify. So you'd use all the techniques that you have at your disposal. On number 3, it says factor and simplify. So in this particular problem, it's giving you a specific technique that has to be used in your work. If you don't use that technique in your work, then you haven't answered the question. So you would definitely have to factor this trinomial first and then use your simplifying techniques from there. 4 through 6 are just straightforward proofs. So they say verify, and we'll work through those, or we can look at an example of those. And 7 is another simplification, but with a specific instruction. It says use cofunction identities to evaluate it without a calculator. In other words, use the cofunction identities to simplify without using a calculator. So those are the problems we're going to talk through here, and make sure everybody has some good strategies for running into these kind of problems on the test. Okay, so the first one is to rewrite and not have a fraction when you're finished. That's the goal. Use your simplifying techniques, but when you're finished, no fraction there. So here's where I'm starting with. That's what's given. And if you remember way back when we did simplifying, we talked about multiplying by a conjugate or a fraction that's equal to 1. So that's what we're doing here. Oftentimes I see students right here try to make a replacement right here and say that's cosine x because they're confused with their Pythagorean identities. Pythagorean identities have a power of 2. This doesn't. That means this does not equal cosine x. So you cannot make that replacement. It would give you an incorrect answer. So I'm multiplying the bottom and the top by 1 minus sine x, the conjugate to this, which remember is a binomial that's only differed by the sign. So here's a plus, here's a minus. And then the numerator has to be the same thing because this has to be a fraction equivalent to 1, so we don't change the value of the problem. So what happens then is this ends up being like the difference of squares on the bottom. So we multiply the 1 together, then we would get negative sine x, and we get positive sine x, which are going to eliminate. And then we would get minus sine squared x. And now we do have a Pythagorean identity on the bottom, so we can make a identity replacement at this point, but we can't make it here. So I'm going to replace my denominator with cosine squared x. Nothing's happening to my numerator. This is a single denominator on bottom, 2 pieces on top connected by a minus. So what I have here is a common denominator. So I'm going to spread this fraction back out into the 2 denominators that would have combined together to give me this single fraction. And then I'm looking at this part, and I'm looking at this part. Remember, we're simplifying, so we can do more than one thing in a step. So I said, all right, here's a reciprocal identity. And sine x over cosine x is the same thing as sine x cosine x times 1 over cosine x. Because remember, there's 2 cosines on the bottom, and there's a single sign on top. So the multiplying 2 fractions together, that would have to be a 1. Okay, so the purpose of this, remember, is splitting it up because we're trying to get rid of the fractions. So what happens now is we have this secant squared x here. We have a quotient identity here, so that's just minus tan x. We have a reciprocal identity here, so now it's just secant x. And you can see at this point there are no fractions. I am finished. Stop here. Be very careful. Don't just be putting identities in to be putting identities in, because if you got to here and you were correct, and you made an error in the next step, then you've now invalidated all your work because now your answer's wrong. And if you just stopped right here, it would be correct. So make sure you're paying attention to what those directions are asking you to do, and you do exactly what it is expecting you to do. On number 2, you have a lot more freedom on this one because it's not giving you anything specific. It's just saying simplify it. So I can see that I have a Pythagorean identity right here. So I replaced this with my cosine squared x. And then I said, okay, I know this is a reciprocal identity, so I have it here. Because I'm simplifying, markouts are okay. So I got rid of my cosine squared x. I don't have to show that it's 1 when I'm simplifying. And so that leaves me with an answer of 1. So remember, you can do cross out things like this when you're doing simplifying, where you cannot when you're doing a proof. All right, so then the next one says to factor and simplify. And so factoring must happen, and I would do that first. So this trinomial, tan to the 4th x plus 2 tan squared x plus 1, is a perfect square trinomial, and it factors to tan squared x plus 1, tan squared x plus 1. If you're still stumbling or you're on a test and you know how you have those moments where sometimes things go, I know how to do this, but I can't think of it right now. Remember, you can turn this back into a polynomial for a think stage. In other words, the thinking thoughts are not part of your work or your problem, but you could think of this as x to the 4th plus 2x squared plus 1, which would factor to x squared plus 1, x squared plus 1, and my x is just this tangent right here. And so then I can go back to my problem with the correct factorization, because if you put x squared plus 1, x squared plus 1 in your work, that's technically incorrect. All right, so now I have my factorization. I see Pythagorean identities here and here, so I make that substitution. And when I multiply like bases, I add the exponents, so my answer is secant to the 4th x. All right, moving on to a verifying. So now we're looking at some proofs. So on this one, remember the form is the first thing you do is write down what it is you're trying to prove. So here's what the problem is. And then I decide which one of these two sides I want to work on, and I write that down, and I put my equal sign. Up to this point, this and this, I haven't even started the problem yet. The first step of my proof is right here. If you do not follow this proof form, you have not worked the proof as expected, and that is really going to be a drastic point loss. So make sure, write it down, pick a side, put an equal sign, now start your proof. All right, so the first thing I did is replace the Pythagorean identity right here. And then I said, okay, that factors, so I went ahead and factored that out. Then I noticed that these two things are the same thing, so I rewrote the numerator so it does look like the denominator. I remember that just means times 1. So now I can see I have a 1. That's what that is. All of this stuff is left. All right, once I'm there, I can use a reciprocal identity. So I'm right here, and I still have my minus 1. So I have to get these two things together as a single fraction. So I need a common denominator. So I'm going to rewrite the 1 so that it's a fraction with a common denominator of sine x, which means sine x over sine x. So now that I have a common denominator, I can put them together with a common denominator and bottom, move my numerators together, and this was the other side of my proof right here. So remember, this is what I started with. So you see this here, you see your equal sign. That's how I start the proof. And then this is the end right here. All right, so the next one, number 5. So on number 5, we have secant x minus cosine x equals sine x tan x. So I write down what it is I'm trying to prove. I pick the side I want to work from, so I pick this one, equals, and now I start my proof. So I use a reciprocal identity here, 1 over cosine x minus cosine x over 1. I know I need to combine these two fractions together, so I need to get a common denominator. So the common denominator has to be cosine x. So I multiplied the bottom and the top by cosine x, and now I have cosine squared x over cosine x. Now that they have a common denominator, I can move the numerators together, and I can make it into a single fraction. Once I have my single fraction, hopefully you can see right there that we have another Pythagorean identity. So I replace that with sine squared x cosine x. And that means sine x, cosine x times 1. And remember, I'm trying to prove sine then tangent. So here is actually my tangent, so I moved it to the back. I moved my sine to the front, and then I can make my quotient replacement right here, and I have what I was trying to prove. So remember, I picked this side to start with here. This is where I have to end at the end of my proof, which is what I did. All right, so hopefully that helps on 5. On 6, this is a little bit longer proof, so you kind of have to be diligent with your notation along the way. Make sure you don't leave anything out. You start by writing down what it is you're trying to prove. Pick a side. So I picked this side, write my equal sign, and now I can begin my proof. So I pulled my numerator off. I separated my numerator from the denominator. So here's the numerator times 1 over the denominator. Nothing's happening to the 1 yet. In the numerator, I replaced cotangent with the quotient identity. And then I could put these two pieces, because it's multiplication, together. So now I have a fraction for the numerator part that I pulled off and reworked. And here's the denominator part that I haven't done anything with, and the 1 that I had in the original part. All right, so this is multiplication, so I can multiply the numerators, multiply the denominators together, and that's what that fraction is, minus 1. I haven't done anything with the minus 1 yet. I need to get these two things together, so I need common denominator so I can put my fractions together. So the common denominator should be the one that's right here, sine theta times 1 minus sine theta. So I changed the 1 to a fraction with a common denominator, so the same on the top and the bottom, and remember that all this equals 1. So now that I have a common denominator, I can move my numerators together, so that's what all this stuff is with my common denominator. Okay, so now I'm down to a single fraction, so I'm getting there. I need to distribute right here so that I can have my pieces to put together. So I do negative sine theta times 1, that gives me negative sine theta, and I do negative sine theta times negative sine theta, which gives me positive sine squared theta, all over this denominator. Now, hopefully, as you look at this, you go, oh, look, there's that Pythagorean identity. However, remember, this is a proof, so we have to show it. If it were simplifying, you could just kind of mark that out and put a 1 in your problem. But since we're proving, I need to move that sign up there so that I can actually show that identity right here and make that replacement in the next step with a 1. So nothing's happened with the minus sine x. Still have my common denominator. So hopefully you see that this is a factor with this. Sometimes people will write it so it looks like a factor. Sometimes people will go straight from here down to this step, and that's okay too. So what I did is I took the 1 minus sine x and moved it over 1 minus sine x from the bottom, and then that leaves me with a 1 times sine x on this side, 1 times sine x. So, sorry, move that up a little bit. So now that I have this separated, because remember all of this is just 1 times all of this, so all of this goes here, and the 1 that you would multiply that by goes right there, if you're wondering on that separation. All right, so here's my 1, and here's my 1 over sine theta. I use a reciprocal identity, which is cosecant theta. So remember, here's what I'm proving. This is the side I picked to start with, so that's over here with my equal sign. Now I've went through all of the proof, and this is where I should end, which I did down here. So that's the end of that one. That was a little bit longer of the 3. A few more steps there. All right, and finally, last one, guys. We have 7, which says use cosfunction identities to calculate sine squared 25 plus sine squared 65 without using a calculator. So this is given a specific method, so you must use cofunction identities in your work. So let's kind of go back and review a little bit here in the notes section. When we studied right triangles, that's a 90-degree triangle, which means the other two angles, 30 plus 60, gives me 90 degrees, and they're complementary angles. So in this triangle, sine of 30 degrees is 1/2, and cosine of 60 degrees is 1/2. So that's where that cofunction identity kind of comes from. So we have sine of pi over 2 minus u equals cosine u, or you could think of it as sine 90 minus u equals cosine u. Depends on units that you're using. So in my case, I'm using the 25 and the 65, so I'm going to say 90 minus 25 gives me cosine of 65. So according to my knowledge right here, what that means then is sine of 25 degrees gives me the same value as cosine of 65 degrees. All right, so that means if I think about it in terms of squares, sine squared theta is equal to cosine squared theta. And now I'm going to use my identity to make a replacement with this right here. So this is that cofunction process. So sine squared 25 equals cosine squared 65. And I didn't do anything with the sine squared 65. Okay, so if I'm looking at this, cosine squared an angle plus sine squared an angle means the angle, or both of the thetas, are 65. And if they're both 65, I have a Pythagorean identity. Remember, it's cosine squared theta plus sine squared theta. Thetas are the same, so I can use my Pythagorean identity at this point and know that this equals 1. So I use my cofunction identity here for my replacement, and then I use my Pythagorean identity here to get to my solution. But you would definitely have to show the cofunction substitution to receive credit for a problem like this because it gave you that specific instruction right here. So please make special attention to the details so that you don't miss things unnecessarily. And woohoo, yay, trig is so much fun. It's kind of like a puzzle. So keep in mind some of the things that we reviewed today. Keep in mind what we did in our notes from 5.1 and 5.2. Those are the things that you'll find on your test. It is pretty straightforward. You're simplifying, you're solving, you're showing that you know how to use the theorems, the techniques, the properties, and that you know how to do a proper proof. Thanks so much, guys.